Well, good morning. It's 8:33. We're 3 minutes late getting started, but I was waiting to see if any students were going to show up. It's the 18th of July, 2019. It's supposed to be differential equations class, but unfortunately I'm the only one in the room right now. So we're going to get started from where we are. Any announcements, I'll wait until there's at least a warm body in the room. I normally would ask if there are any questions, but nobody here to ask. So where we left off last time was Chapter 4, Higher Order Differential Equations, 4.1, Preliminary Theory, Linear Equations, and we're in 4.3. We finally finished 4.2. 4.3 is non-homogeneous or homogeneous equations. So, few other bits of nomenclature here. First, a function, let me get my pen set up. Okay. A function y sub p, okay? Now we haven't been calling them sub p's much, so that has a, if it's free of arbitrary parameters, can't spell, arbitrary parameters, okay, that satisfies what they call equation 7, but you have to go way back, if you got a text, to page 121, and this is the one that it's just like our linear nth order differential equation. Looks just like the homogeneous or homogeneous case, except that rather than after the equal sign, where the homogeneous or homogeneous case, you have a 0. On these, you have a g of x. Okay? So, what if you have a y sub p that doesn't have any of these arbitrary parameters in it? It's not one that we're including in our standard set, or I can't remember what I call it. I know one thing, fundamental set of solutions. It doesn't have that arbitrary constant in it, but it satisfies the differential equation. Okay, the DE, and that's the nth order linear differential equation, but not the homogeneous one or homogeneous one, the non-homogeneous one. It's said to be a particular solution this is why they named it that, a particular solution. Okay, a particular solution of the equation. Now, if you have a non-homogeneous or differential equation, y double prime plus 9y is equal to 27, okay, they say it's a straightforward task to show that this function, y sub p equal 9, right? 3, I'm sorry, I got it confused. Y sub p is equal to 3, okay? Clean that up just a little bit. Okay. I'll clean it up a little more. Okay. Y sub p is equal to 3. Well, let's see. 3, first derivative of 3 is 0, second derivative of 3 is 0, and 9 times 3 is 27. It doesn't need an arbitrary constant, C1, C2. In fact, that will make it not true. Only one that would work is C1 equal 1, okay? And you don't need that, okay? Not an arbitrary constant, no constant you need. That obviously solves that equation. Okay? Now, it's a lot like, back on the homogeneous or homogeneous case, remember that y equals 0 always works on those. Well, on this one, y equals 3 happens to work. So this is called a particular solution. Now, what if we had a y sub 1, a y sub 2, a y sub 3, dot, comma, dot, 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 all the way up to and including, this time the counter is k, up to y sub k. And these are solutions of the homogeneous case. When it is equal to 0, okay, on I, the interval I that we're dealing with, and you also have one of these y sub p's, okay, that also satisfy. It's a particular solution. Then the linear combination of y is equal to c1, y1 plus c2, y2. I should be putting my x's in there. They do, I wasn't. Plus c3, y sub 3 of x, plus dot, 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 all the way up to and including c sub k. Yep, y sub k. Why they changed the subscript, I don't know. Y sub k of x, plus you also have to include y sub p. No constant in front of it, just y sub p. If that is also a solution for the non-homogeneous case, then you just add that to the other. Now this is what, for a non-homogeneous system of equation, this is what we call the general solution. And that's what the next theorem states. So let me write that next theorem out. Now I may not have room here, so let me erase this and write it out. Let y sub p, goodness gracious, I can't write today. My screen is fluctuating on me some, but it always does something. Y sub p be any particular solution okay, of the non-homogeneous or non-homogeneous, okay, linear, remember we're dealing with linear, nth order differential equation, DE, okay, on some interval I, and let, just like we did before, y sub 1, y sub 2, y sub 3, comma, dot, 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 all the way up to, and for some reason this time they go back to y sub n. It doesn't matter what you do them, call them. But this be a fundamental set set of solutions of the associated homogeneous or homogeneous differential equation. Okay, now just get the idea. This is the same differential equation, linear nth order differential equation. The non-homogeneous or non-homogeneous case has an equal to some function at the end. They've been calling it g of x. The associated homogeneous differential equation is the precise coefficient functions, the precise order, the precise everything, except after the equal sign it's a 0. Okay? So this is your fundamental set of solutions. Now what do we mean by a fundamental set? These are linearly independent. Okay? And this is the fundamental set of solutions for that associated homogeneous differential equation. Okay, so that's the setup here. On that same interval I, okay, then the general solution, okay, now remember this is a name for the general solution for the non-homogeneous case. The general solution of the equation on the interval okay, is y is equal to, and then all your first, c1, y1 of x, plus c2, y2 of x, plus c3, y3 of x, plus dot, 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 all the way down and including c sub n, y sub n of x, plus your y sub p, okay? And that's a function of x as well, so I'll put that down too. They haven't been done, but I have. Where these CIs, where I is going 1, 2, 3, dot, 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 all the way up to n, okay, or arbitrary constants. Doesn't matter what they are. You can put any constants in there, and that will be a solution. Okay? Now, they do a little proof here, and it's okay. It's not that difficult, but we're running pretty much out of term here, so I'm not going to go over all that. But it's worth a read, and go for it. Now, another definition here. This is called the complementary function. Okay? Now, it's something basically we've already done, but they're just giving it a name now. Okay? So, just because, let me start on a clean page just to keep from crowding things up too much. So, I'll erase all that ink. Okay? In that theorem I just put down there, the general solution of the non-homogeneous linear equation consists of two functions. I should have left it on there. The y was equal to c1, y sub 1, I wish I had left it, okay, plus c2, y sub 2 of x, plus c3, y sub 3 of x, plus dot, 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 plus c sub k, n, I think it was this time, y sub n of x plus y sub p. That happened to be a particular solution. This was your general solution for the non-homogeneous or homogeneous linear equation. Okay? It's the sum of two functions. This part here, which we were calling the general solution for the homogeneous or homogeneous case, this is now called the complementary function. Okay? The complementary function for the non-homogeneous case. It was the general solution for the homogeneous case or homogeneous case. Now it's called the complementary function for the non-homogeneous case, and we just generally will call that y sub c of x. It's that linear combination of all those individual functions. So your general solution for your non-homogeneous case will be the complementary solution plus the particular solution. Okay. In other words, to solve the non-homogeneous linear differential equation, first solve the associated homogeneous equation, then find any particular solution for the non-homogeneous equation, the general solution of the, here he is. Morning. Good. How about you? So, Still,
I woke up this morning not feeling good.
I'm sorry. You look like you don't feel good.
It's fine.
Is it the cold?
Well, sort of. I'm having like migraines and nausea.
Yeah. Bad combination.
Yeah.
All right. We're still in Chapter 4, higher order differential equations. If you really feel bad, you know, I'm recording this. You can. Okay. All right. We're in Chapter 4, higher order differential equations, 4.1, preliminary theory. Still in this on linear equations, and we're into 4.1.3, which is the non-homogeneous or non-homogeneous equations. We got up to this last time, didn't get there. Now, what I've covered so far has been a couple of words, what we mean by a particular solution, and we'll go over that if you need to. And then that contributes to what we call a general solution. And then that backtracks and calls what we were calling the general solution for the homogeneous case or homogeneous case is now being called the complementary function to the non-homogeneous or non-homogeneous case. And so basically it gets, the bottom line of all that, and it was several screens worth of stuff, is this. Now, does light bother you? Okay, I don't know. I've had things close to migraines. Light was not a good thing.
Last night I had a migraine. This morning I had a migraine, but I had nausea, but it's couldn't get really. I mean, it felt like I had to throw up.
Yeah.
But it just nothing came out.
Right.
So I just kind of like sat there.
Right. Yeah.
I came right after that. So.
What's that?
And until I was like ready to go, I just came.
I can't hear, sorry.
When I finished, I
Right.
guess like when I sort of like stopped feeling bad, I was like, all right, let's get the car. So I came in.
Okay. Hope you feel better. All right. So this is the bottom line of what we just done. When you have the non-homogeneous, okay, a little bit of background. You know what the nth order linear differential equation looks like. It's you have some a sub n of x. It can't be 0 for any of the x's in the whole thing, in the whole interval, times your y sub n, the nth derivative of y, and then you step down until you get to the very last one, and then you have a sub 0 times y, and that's equal to 0. That was the homogeneous case. It's equal to 0. But you have some equations that you have an actual function over here. Now, it has to be a function of x. Can't be a function of y. If it is, move it back there and put it in with the y's. But it needs to be a function of x. Well, when you have that, you may have solutions that will make that differential equation work for that particular function here. Then these don't have the c's with them. The c's go with the homogeneous case. Okay? It's a linear combination. It's called a complementary function. Remember, we usually call that the fundamental set of functions that make up that linear combination. And that's what we call for the general solution for the homogeneous case. Now we call it the complementary solution for the non-homogeneous case, or homogeneous case. Then these particular solutions that work just for that g of x, they don't have the c's with them. They're just solutions for that, okay? So then your general solution for your non-homogeneous or homogeneous case will be y is equal to what was your general solution for the homogeneous case, which is now called the complementary function, plus any of these particular functions. So that's the bottom line of what I've been doing so far. We're just ready to do example 10. Hopefully it might make a little more sense now. Not that it didn't make great sense to you to begin with, but let's do example 10. Now, I hate that they start the thing by substitution, the function blah, 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 okay, is readily shown to be a particular solution of this. Well, I'll write it down. There, see, later we're going to find these ourselves. Now they give them to us and say, it can be shown this is, okay? Why don't they just tell you how to get them first? But they don't do it that way in this book. Y sub p, this they're saying is a particular solution. And isn't it a fun one? Minus 11/12, that's starting good, minus 1/2 x, okay? They say that can be readily shown to be a particular solution of this non-homogeneous equation. Here's the equation. Y double prime, no, that's a triple prime, minus 6y double prime, plus 11y prime, minus 6y is equal to 3x. Okay. Now, that's a linear, third order, ordinary differential equation, but non-homogeneous because it has a function at the end. It's not zero. It's non-homogeneous. Okay? Now they're telling us this will be a particular solution for that. Not for the left-hand side, but the left-hand side makes the right-hand side what it is. So what we have to do is do our yp prime, which would be what? Negative 1/2, you got it. Now how about yp double prime? 0. And yp triple prime will also be 0. Okay? So let's see if their statement was true. This would be 0, that would be 0, and here you would have 11 times negative 1/2 plus, minus 6 times negative 11/12 minus 1/2 x. Isn't that a beautiful function? Is that equal to 3x? Okay. Pretty easy to verify. This would be minus 11/2, right? And this would be plus 11/2, right?
Wouldn't it be 66?
Second?
Wouldn't it be 66 over 12?
66 over 12, you're absolutely right. Now divide numerator by 6. And divide denominator by 6, right? Good deal. Okay? And plus 3x. And then, sure enough, that's equal to 3x because these two add to 0. Okay, so this particular solution up there solves this non-homogeneous differential equation for that g of x, the 3x at the end. Guess what? It has nothing to do with the solution of the homogeneous case. Nothing, absolutely nothing. When we solve that, you'll see it doesn't look anything like a linear equation like that one is. Okay, so to write the general equation solution for that equation then, this one right here, this differential equation, to write the general solution, we must be able to solve the associated homogeneous equation, which is y triple prime minus 6y double prime plus 11y prime minus 6y equal what? 0, because that's the homogeneous case or homogeneous case. Now, if you go back to example 9, you'll see they came up with 3 solutions there for that very case. You don't have your book on you, but it did. And we found out they were linear. They were linearly independent of each other. We did the Wronskian for them. And we concluded that y is equal to C1 e to the x plus C2 e to the 2x plus C3 e to the 3x, okay, was the general solution for that differential equation, the homogeneous case. And since that was the general solution for the homogeneous case, we now call it y sub c, the complementary solution for the non-homogeneous case of that same thing on the left. So now your general solution for your non-homogeneous case that we're given here would be same as this, C1 e to the x plus C2 e to the 2x plus C3 e to the 3x plus your particular solution, which was actually, in this case, minus 11/12 minus 1/2 x. Okay? That's your general solution. Okay? Notice these terms here don't have arbitrary constants. These do, because that's the general solution for your homogeneous case. This is a particular solution that works with this function at the end. And since it does work for that, you leave it alone. If you put a constant in front of it, it's not going to solve that. Okay? This one solves it. Okay? So that's your general solution for that non-homogeneous or non-homogeneous differential equation. You do the homogeneous part, and that has your arbitrary constants in it, and then you do the the right-hand side, find what satisfies that, and just add it to the others. Okay, that's the procedure. Okay. Now, and as I said before, notice this doesn't look anything like any of those, okay? And it shouldn't. It doesn't need to. Occasionally it might, but it doesn't need to be anything similar to them. And therefore it's not part of the general solution for the right-hand side, the homogeneous part. So this leads to another superposition principle, and we're going to use this later when we are finding those particular solutions for the non-homogeneous case, when we finally get around to doing that. And here's the theorem. So I'll erase this. Can I erase it? Okay. Okay. It's the superposition principle for the non-homogeneous or non-homogeneous equations. What if you had a series of them? And you could. Y sub p sub 1, y sub p sub 2, y sub p sub 3, ... up to and including what they're going to use the counter here, k, y sub p sub k, be k particular solution of the non-homogeneous linear nth order differential equation of the non-homogeneous linear nth order differential equation, like we had there. They keep referring to equation 7, on an interval I, corresponding in turn to k distinct functions. G1 of x, G2 of x, G3 of x, dot, 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 up to and including G sub k of x. Okay? Okay. Because guess what? Remember, the left-hand side of is the homogeneous part. On the right-hand side, we had a g of x. Well, that was a really long, complicated g of x. All functions of x, we say e to the x plus log 7 e to the log 7x plus cosine squared x plus, you can just keep adding things there. Well, these would be your various g of x's. It's still a function of x, but it's made up of a whole bunch of different functions of x. You can still do this, okay? And if these are your particular solutions that correspond to each of those pieces of your g of x, up to k pieces, however many you happen to have, okay, that's the given, okay? That is, suppose y sub p sub I denotes a particular solution for that non-homogeneous equation if that was the only g sub I of x was the only one that was there. Now you have a whole bunch of them, so your overall particular solution as a function of x for that one that has all these g's on it would be y sub p 1 of x plus y sub p sub 2 of x plus y sub p sub 3 of x plus dot, 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 up to and including so y sub p sub k of x. Now, the difference here is no constants. There's no arbitrary constants you put in there. If you find a particular solution that works for this thing, it just goes there. It's not some linear combination of them. It goes there, and they just get added together. No arbitrary constants, okay? And this would be then the solution if all these things were added together, okay? That would be your particular solution for that. Now, there is a little proof here, and you can certainly go through the proof. Let's do this with example 11. This is the last example in the section, finally. And it says you should verify, so we will, that y sub p sub 1 is equal to minus 4x squared is a particular solution of this equation. Y double prime minus 3y prime plus 4y is equal to minus 16x squared plus 24x minus 8, that differential equation, that non-homogeneous differential equation, where that's one function g of x, okay? They also claim that y sub p sub 2 be e to the 2x is a particular solution of that very same differential equation here, but now, except that it has a different g of x. This time it's 2e to the 2x. Okay? And that y sub p sub 3 equal xe to the x is a particular solution to this same non-homogeneous part, the first part, has exactly the same, but this time on the right-hand side, you have 2x e to the x minus e to the x as your particular solution. Now, I can almost hear you asking, though I can't quite make it out, how do you know this is one equation and not three? How, that obviously is one. How do you know this is two, is one or two? Well, do what works. We'll get to that later, okay? We will. Ultimately, we'll get there. Okay. Now, what we need to do is verify that all three of those statements are true. So let's do it with y sub p1 first.
It's true.
Say again?
I think I see where it's true.
I can't hear you.
I think I see where it's true.
Yeah. Okay. You really good.
Take the derivative.
Yeah. Y sub p1 prime would be
32x plus.
Say again?
32, negative 32x.
Whoa.
Oh, I looked at it wrong.
Yeah.
Negative 8x.
Good. Okay. And y sub p1 double prime would be negative 8. And that's all we have. Okay. So let's plug that in here. And this would be a negative 8 minus 3 times.
24x.
Okay, that'd be plus 24x. Okay, yeah, no, that's fine to do it. Okay. I don't want to do it because I'm afraid I'll lose you or lose a student. I don't think I could lose you. So that plus 24x, right? Minus 16x squared. And sure enough, ding, ding, ding. Yep. This is a particular solution for this differential equation with that g of x. Okay, let's do the same thing for the next one. Y sub p sub 2 prime would be 2e to the 2x, and y sub p sub 2 double prime would be 4e to the 2x. So let's plug and chug here. That would be 4e to the 2x minus 6 e to the 2x plus 4 e to the 2x. And is that equal to 2e to the 2x? Yes, it is. So that is a particular solution there. Now let's do the third one. Y sub p sub 3 prime would be, what's that?
It's going to be doing something worked out in my head. All right, e to the x plus x e to the x.
E to the x plus x e to the x. You worked it out really well in that sore head of yours. Y double prime p sub 3 is equal to e to the x plus e to the x plus x e to the x. Your old head is working pretty well, which I'm going to shorten to be 2e to the x plus x e to the x. Now you could also do 2 plus x times e to the x, but I don't think that's particularly helpful here, but we'll see. Okay? Now, let's take that and plug it in here. That's your y double prime, which is 2e to the x plus x e to the x. That's the y double prime. Minus 3 times this will be minus 3 e to the x minus 3x e to the x. And then 4 times this would be plus 4x e to the x. Agreed? Okay, pretty exciting stuff, isn't it? is that equal to, well, let's see what it's equal to. Here we have a 2e to the x minus 3e to the x. That's minus e to the x.
Yeah.
Right?
Yeah.
So that takes care of those two. And here we have 1 and 4 are 5. Minus 3 is plus 2x e to the x. And sure enough, that's what we got. Okay? So, those three particular solutions work for those three g of x's, right? Now, I'm going to erase all of our verification here. You okay with that? You don't care, okay.
So would this be generally just what we do?
What you say?
But generally what we do if we get a problem, it's just confirm it.
Okay, is what? I couldn't hear.
When we get a problem, all we're doing is just confirming it.
That's 4.1. Starting in 4.2, I believe. .2 is very short, reduction of order. 4.3, we're going to start solving them. So,
This is just confirming it.
what's that?
We're not solving them here, we're just confirming.
Right now, we're just confirming, and you're getting the principles down, I guess is how they see it, and then we'll do the solutions, and we'll know how to put them together and make them work. Seems like to me they could have shown us that while we were showing us how to solve them, but they chose not to. Okay. Now, what now follows is, what if you had this as your differential equation? Y double prime minus 3y prime plus 4y equal minus 16x squared plus 24x minus 8 plus 2e to the 2x plus 2x e to the x minus e to the x. What if that was your differential equation? Certainly non-homogeneous, right? Look at all that mess on the right-hand side, okay? But you see this part here is that, this part here is that, and this part here is that. That could be your differential equation, okay? And if it is, then, and it is, okay, oh, I'm sorry. I guess I should have said, well, I'll get to it. Okay, that's your differential equation, and it follows from that that your particular solution of that differential equation, this is not the complementary, this is not the homogeneous part, just the right-hand side. It's the left-hand side, but as applied to that, would be minus 4x squared plus e to the 2x plus x e to the x. That will be your particular solution for this differential equation, because this part does that one, this one does that one, and these part are done by that. Okay? So, your general solution, y, is going to be your y sub c, whatever complementary part handles that if you set it up to be a homogeneous or homogeneous part. Whatever that turns out to be, and then you'll add to that your y sub p, which is made up of these parts. This part, y sub c, will have arbitrary constants in it. Now, the sub c means complementary, but think of that as it has constants. The particular parts does not. Okay? Now, what if this equation here had some arbitrary constant in front of it? Then your particular solution that corresponds to that would have a constant in front of it. But it must be the same constant that was in front of that right here. Okay? And the same thing here. That with a 2 in front of it now, if it didn't have the 2, this would have been a 1/2 in front of that one. Okay? So, what they're saying here, you can have constants in front of those particular solutions only if those G's had constants in front of them. Okay. And it says, before we actually start solving homogeneous and non-homogeneous linear differential equations, we need one additional bit of theory, which is presented next, which is coming up. Now, one more thing. These remarks. That expression we had before that looks a lot like this, okay? A sub n of t, now, this is something that's rather bizarre. Now they're putting t's in rather than x's. And when they do that, usually that indicates they're talking about time, not displacement, okay? So if you had t's in instead of x's, y is a function of t rather than of x, and you had that thing, that's said to be an nth order linear system. The n time-dependent functions, the a sub n, of t, a sub n minus 1 of t, a sub n, okay, I'm sorry. The y of t, y prime of t, and y, I'm sorry, yeah, are said to be the state variables, and their values at some time t is said to be the state of the system. The function g of t is called the input function or the forcing function that drives this thing, okay? The solution y of t of the differential equation is said the output or response of the system. Now, you're probably not, well, you might get into a little bit of stuff similar to industrial engineering in what you're doing, because you are going to be looking at what is causing this and what's the effect of this, okay? So in some senses, these drivers and output response may pertain something to you. I don't know. I don't know your field well enough to know that. Okay, so anyway, that's it. So homework exercises, going back to 4.1.1, do any of the odds, either 1 or 3, if they're in the back of the book. Any of the odds, either 5 or 7 if they're in the back. Number 9 if it's in the back. Number 11 if it's in the back. Number 13 if it's in the back. 4.1.2, the homogeneous or homogeneous parts. Any of the odds 15 to 21 if they're in the back. 23 to 29 if they're in the back. And then for the 4.1.3, the ones we just did today, either 31 or 33 if those are in the back. 35 if it's in the back. Now, generally the discussion problems are not, but if you do find some that are, you might want to look at those as well. So what was that one other little bit of theory we needed? That's in 4.2, okay? And this is called reduction of order, okay? Now, what if we had a second order differential equation? So that would look like this. A sub 2, we're going back to x now, y double prime plus a sub 1 of x, y prime, plus a sub 0 of x, y, is equal to 0. Homogeneous or homogeneous, okay? Homogeneous, linear, second order differential equation. The general solution could have easily been something that looked like this. It would be something that looked like this. Y is equal to C1 times Y1 of X. Well, they don't put the X's anymore, plus C2 Y2. All these are functions of X. C's are not, but the Y's are. Where Y1 and Y2 are solutions that can constitute a linearly independent set on some interval I. Okay? They're linearly independent. There's got to be some set like that. Second order, you need two constants. Okay? Now, beginning in the next section, we examine a method for determining these solutions when the coefficients of the differential equations are constants. So that's where we're going next, when you have constant coefficients. Not functions of x like a sub 2 of x, just an a sub 2. Not an a1 of x, just an a1. Not an a0 of x, just an a0. Just constants. Okay? That method, which is a straightforward exercise in algebra, breaks down in a few cases and yields only a single solution y1, rather than y1 and y2. It turns out that we can construct a second solution, y2, of a homogeneous equation, even when the coefficients are variable, okay, provided we know the non-trivial solution, y1, of the differential equation. Basic idea described in this section is that equation 1 can be reduced to a linear first-order differential equation, meaning by means of a substitution of involving the known quantity y1 that we just got. The second solution is apparent after that first-order differential equation is solved. They say so, anyway. This is called reduction of order. Okay? Suppose that y1 denotes a non-trivial solution of this equation. So let's say we have a y1 we know works there. Okay? On some interval I. Okay? We seek a second y2 so that the set consists of y1 and y2 are linearly independent on that interval I. Recall from section 4.1 that if they're linearly independent, then the quotient y2 over y1 is a non-constant on that interval. So if y1 and y2 linearly independent, that implies that y1 over y2 is not a constant. Okay? All right. On I. Okay? Or they said y2 over y1. Okay? So let me do it the same way they do so it doesn't get confusing. Doesn't matter which one you put on top, but let me do it the same nomenclature they do. Okay. All right. Well, let's name that ratio that's not a constant to be some u. Did they put a subscript on it? I don't think so. U of x. Now there you do put an x in there, and the reason is it's not a constant. If that was a constant, you wouldn't need the x in there. Okay? So this is some function of x, not a constant function. Okay? Now, what you could do is rewrite this as y2 is equal to y1 times u of x, right? Just multiply both sides by the denominator. And by the way, y1 is also a function of x, and y2 is a function of x. They didn't write it there, but it is. They are. Okay? The function u can be found by substituting that into the differential equation, and that method is called reduction of order. Okay. Blah, blah, blah. Right? So let's do what they just told us. Let's do it in an example. Here's a given. y1 is equal to e to the x. Okay? And the claim is this is a solution to this differential equation. Y double prime minus y equals 0. Well, let's make sure that's true. What's y prime? y1 prime? What's y1 double prime? And e to the x minus e to the x, sure enough, is 0, right? So, we know that's the solution. Okay. And that's the solution everywhere. On minus infinity to infinity. It's good everywhere. E to the x is good everywhere. Okay? Now, that's the second order differential equation, but we can't come up with that one solution. Okay? So here's what we're going to do. We're going to say y2 is equal to some u of x times e to the x, times that y1. Okay? Now, let's take its derivatives. y2 prime is equal to what? Good old product rule.
Is that u? Is that supposed to be like u?
It's not a mu, it's a u, but it doesn't matter. You could call it mu if you wanted to. But it's not our integrating factor, if that's what you're asking. It's just some function u.
Well, then it'd just be u of x times e to the x.
U of x times e to the x.
And I guess
Second,
plus
plus
e to the x.
e to the x.
U prime.
U prime of x. Perfect. Okay, what's y2 double prime? Yeah.
U prime to the x.
U prime of x,
E to the x.
e to the x,
Plus
plus
e to the x.
u of x,
E to the x.
e to the x, plus,
U prime.
second, u prime of x,
E to the x.
e to the x, plus
U double prime.
u double prime of x, e to the x. Okay? Now, if not, I'm not seriously mistaken, that's, you can factor out e to the x. Now, I think they do, but let me confirm that first. Okay? They're leaving it in for now, so let's do it. But let's simplify a little bit, because you got 2 of this term and 1 of the other 2. So I'm going to write it this way. U double prime of x e to the x plus 2u prime of x e to the x plus u of x e to the x. Okay? So that's our y double prime. So let's plug this back into our original equation. U double prime of x e to the x plus 2u prime of x e to the x plus u of x e to the x minus what the original function was. There it is right there. U of x e to the x. All right. Now what does that do for us? That wipes out this one. And this is supposed to be 0, right? Now, they got e to the x's in there. They can't be 0, so you can factor them out and throw them away. And now you get u double prime of x plus 2u prime of x is equal to 0. Okay? Because of the differential equation. All right. Now, here's where things get a little squirrely. And this is why they call it reduction of order. Because now we do this. Let's let w equal u to the u prime of x. That look like a legal move?
I'd say I'm just really confused because I'm looking at the y double prime minus y. I know that's solution, right?
Okay. Oh, let me stand up. All right. You're getting the y double prime from this one, right?
Yes, sir.
And you're, yeah.
The y double prime minus y.
Minus, oh, yeah. That's your original equation. That's your differential equation. That's the solution to it.
But it doesn't equal 0.
Yeah, it is. Y double prime minus y is equal to 0. So homogeneous.
To u of x?
Huh?
For the u of x problem or for the y?
Okay, okay. This is your original problem. We know that this is a solution to that. We verified it, right? But this is a second order differential equation. It needs two linearly independent solutions because it's second order. So we're looking for the second one. So here's what we're going to use. The second one is going to be some u of x. We don't know what it is. Some u of x multiplied by this one. Okay? You all right with that? We're going to say that will be our second solution. Well, if it's a solution, it has to satisfy that, doesn't it? So we need to do what y prime is, and you did that correctly, and then the y double prime. And do you agree with that? Okay? And that you could combine these two terms and get that? All right. So this is your y2 double prime. We're going to put in here. This plus 2 of these plus that one. Then minus your y, and this is your y2 now, which is this, u of x e to the x. I'm sorry, minus u of x e to the x. Well, now this last term from this one and this term add to 0. So that leaves us with this. U double prime e to the x plus 2u prime e to the x, okay, is equal to 0. Because those two add to 0.
So now we're going to let w equal u prime of x.
Yeah. And the reason we're doing that is because, you see, we now no longer have the u term here.
And we factored out the e to the x.
We factored out the e to the x because it's never 0, right? It's always positive. Always positive. So you can factor it out, divide it out, and it's out of it. So here's what we're going to do. Let w be u prime. Then what would w prime be?
It would be u double prime.
U double prime.
So
Okay.
w prime plus 2w.
All right, you got it. Your new equation becomes w prime of x plus 2w of x is equal to 0. Right?
This is just off topic, but what would u prime times u prime, would that equal u double prime?
Okay, say that one more time.
U prime times u prime.
No. That would be u prime squared.
Okay.
Yeah. U double prime is the second derivative of u with respect to x, or whatever the independent variable is. All right. Now, this is something. Let's write this as dw dx, isn't that plus 2w of x is equal to 0. Okay? Now let's write that as dw dx is equal to minus 2w of x, right? Legal so far? Okay. Now let's take that and do. Hey, look at that. Oh, well, close. Let's do dw over w is equal to minus 2.
Okay, you got to explain.
Minus 2 dx. Sorry.
So did you swap them?
What's that?
You swap the dx with the w of x?
Okay, that's a w. Okay.
Did you swap the dx with the w of x?
Yeah, that's sort of what we did. We wrote it in differential form and divided by the w. Yeah.
Why didn't you write w of x then?
Well,
I mean, you don't have to.
just reminding you, it's a function of x. Okay.
Sorry.
Okay. But now we can integrate both sides. That's what you were suggesting, wasn't it? Okay. So integrate this and integrate this.
W is dependent on x, right?
Yeah, right. But the left-hand side is all W's, and what's the antiderivative of W? Of dW over W? Oh, no, okay. Do this one.
Oh, sorry. That's just going to be W.
Is what?
Would it just be W? WX? WY?
Wait. Isn't that log W? dW over W?
Yeah, I was looking at the DW, my bad.
Okay. So what's that going to be?
ln of W.
Of W is equal to, and yeah, that's a factor of X, yeah.
2X. Negative 2.
Negative 2X. Okay? Now, we can exponentiate both sides, and we get, pretty exciting, isn't it? The W of X is equal to e to the minus 2X.
Yeah. I agree with that.
I can sell you swampland in Florida, can't I? Okay. Now,
Are we going to go back and say?
yeah. Okay. That's what your W is, which is what your U prime is. So, du dx is equal to e to the minus 2x. Right? And then just do your dx over here, and this will give you u being
I'm sorry, would it just be?
You integrated both sides. That was just a du, so it became a u. And it's u of x, if you want to put that in there.
To the negative 2x?
It's what? E to the minus 2x for sure.
I forget how to.
You unchain rule it over a negative 2. So this would be minus 1/2 e to the minus 2x. Now, we also have some plus c's in here. And I've been leaving those out, probably not well, but I've been doing it. And I probably should have, when we did this integral down here, we should have had a plus c with it. And let me make sure. I should have taken care of it up here when I had it, when I was doing the integrals. It came out to be a constant here when you integrated this, wasn't it? Oh, when I integrated this, yeah, there it is. Okay, log W is equal to minus 2x plus c. Now they call it plus c1, okay? Now when you exponentiate that, you get the W of x is equal to e to the minus 2x plus c1, right? Is that right? Okay. Now, but you see, you could also write that as e to the minus 2x times e to the c1, right? Okay. And this is just a constant. So why don't you just write it as c1, it's a different c1, e to the minus 2x. That should have been what I integrated here. Put a c1 in here and a c1 in here. But then you have to have another c2 when you do that integration, because you have this c1 here. God, this thing keeps flopping on me. Sorry, I'm having to make up for bad behavior before. Okay? And that gets us down to where we are here. Okay. Now, that's what your u is. Now, I need to erase some stuff. Well, maybe I can write it down here. Let me write it again. U of x is equal to minus 1/2 C1 e to the minus 2x plus C2. All right. Well, what was our u of x? The u of x was, you multiply that by e to the x to get your y2. So my y2 here of x is equal to that multiplied by e to the x. So we have a minus 1/2 C1. Now e to the x.
Now, are we making it 1/2? What told you to make it 1/2?
That was from up here.
Okay, sorry.
And up here. Okay, I just brought it down there. Okay, when we multiply this thing by e to the x, that drops that to be e to the minus x, right?
Yes.
Plus C2 e to the x. Okay. So there is our new y2. It is. Okay.
So basically, we set w up equal to u prime, and then we found what w was.
Okay. Well, you did a lot before you got there.
Well, I know you did a lot.
Okay. But yeah, once you got to that stage and you lost the u's here, then you can do a substitution, bring it down to a linear equation. And that linear equation can be solved by separation of variables, and you just go to town with that then. Yeah. Is that what you're saying?
Yes, sir. I was just basically, yeah.
Right. Sort of summarizing. Okay. Now, here's the part that gets, to me, rather strange, as if most of this isn't strange. I need to erase a bunch, and I can't get there it is, okay. I want to erase a bunch, but I don't want to erase anything that's absolutely necessary. So let me start. I don't know where to start. Let's just start here and erase this. Okay, I don't want to lose my answer here. I'm going to erase that too. This is pretty exciting watching this disappear, isn't it? Whoa, I almost erased too much. Okay. All right. Bottom line is then, we came up with, after all that work, we came up with our y sub 2 of x is equal to minus 1/2 C1 e to the minus x plus C2 e to the x. And I could have erased this part too. That's just in the way. And now that I've written that, I can erase this down here at the bottom too. Okay. So there's our y2. We had a y1 e to the x, and here's a y2 of x. Negative 1/2 C1 e to the x plus C2e to the x. Okay. Now, here's the part that kind of drives me nuts. They say, by choosing C2 equals 0 and C1 equal -2. I say, wait a minute, why do you choose that? Okay, now those are constants of integration, and I guess they're arbitrary, so I guess you could choose either one, but they just leave you hanging and say, by doing this, we obtained the desired second solution. Well, who said that was what we desired? I mean, they leave a lot out. Now, here's what I prefer to do. Looking at this one is just like y1, right? So that's the reason to choose that C2 equals 0. We don't want to duplicate y1. Now, why did they choose C1 equal 2? So you could get rid of your fraction. Okay? Why didn't they do a -2? I don't know. Okay? They should have in my book, but they chose no, they did do a -2 to get rid of the minus sign 2. So rather than saying we just choose this, those are the reasons. So your y2 of x can then be e to the minus x. Okay? Okay. Because who needs the C1? Who needs the 1/2? Who needs the minus sign? You really don't. This is what you need. And you don't need the C2 because you already got that covered with that. Okay? Now, because we're going to turn around and put arbitrary constants in front of that anyway. So now we've come up with a second solution, that. And obviously, these two are linearly independent. Okay? This doesn't contribute anything to linear independence. In fact, that could be dependent. So that's why we chose that to be 0. Okay? So here's your solution.
Is it ln or e that can't go below 0?
E doesn't go below 0. Ln, you can't take the log of 0 or anything to the left of it.
Why is it negative infinity to it? Why is it negative infinity?
Okay, wait. Okay. E to the x can. Here's
it can't go below 0.
Yeah, but this is what your domain is. Now, if it had been log, then for sure you'd have to be greater than 0.
Would it have been asymptote?
Yeah, that would have been a vertical asymptote. Yeah. And if this would have been log, like this one, this is log x, then x had to be, the interval would have been 0 to infinity, the input, because you can't include 0, so therefore you don't. I don't know why it did that. Okay. You can't include the 0. Okay. But for e to the x, yeah, the input can be anything. All right. Now, that was it for example 1. Well, okay. Okay, take a break. All right. I'm about to burst. So. All right. The question came up, what's the rest of the term looking like? And I found this strange, but I guess it's true. This is the day, the 18th. We have class Tuesday and Thursday of next week, and that's all, folks. Because I'll give you the last test.
Wait, you can withdraw on the 25th? That's the last day to withdraw?
I know. Isn't that ridiculous?
If you made it that far, I'll just go ahead and finish the class, you know?
Well, if you got an F, better to withdraw.
No, do you just get a W on your
You just get a W.
No W. And then after that, you get a WF on.
No, well, I don't even think they do WFs anymore. It's either a W or an F.
Yeah.
If you withdraw by this date, you get a W. If you don't, you get an F. If you're failing. Yeah. I know it's ridiculous. Okay. So I'll give you your test on the 25th, the last test, and it'll be due back either the 30th or 31st. Let's just see what August looks like. I thought we had the finals would be Wednesday and Thursday, not
Tuesday.
Okay. Here's August. See, this is ridiculous. The final we have no need for final exams on Tuesday and Thursday because no classes overlap. All the final, because this is the final exam day for regular term, we're going to have class on Tuesday.
That's fine.
Yeah. And I'll give you the final that day and try to have it back then.
That's fine.
It's going to be pretty short and you're able to do. But I'll still be here on Friday, so you can get it to me even Friday morning, because I won't be here past noon on Friday. I'm trying to take off on Monday because we need to go to Georgia.
To the farm?
Yeah. And so there's no reason to have two final exam days here. That's what I thought. I thought that we're going to have a class on Tuesday the 30th, and then I'll give you your final on that day, and then you'll have get it into the 31st, the 1st, or the 2nd. But if it's the 2nd, I have to have it before noon on the 2nd, because I've got to get my grades in by the 2nd, because I won't try to take Monday off. Okay. That includes the papers. Okay. All right. I need those before the final exam day, by the last day of class.
So the 30th.
Yeah, now the 30th, yeah.
I'll give it to you.
Huh?
I still got time. There's no difference between me turning it in right now and then next week.
Except that if everybody does that, I've got that many to grade next week. So there is a little difference. Not to you, but to me. Okay. And maybe I should phrase it this way. I might be a little more irritated next week, mightn't I, if I get them all in.
Just pull this paper real quick out of my notebook.
What's that?
Let me pull the papers out of the notebook real quick. Here you go. You guys irritated now?
Okay. If you handed it to me, I wouldn't be. Okay.
I'm sorry.
No, I'm not. Yeah.
I understand.
Yeah. All right. Now, we did example 1 on the bottom of page 132, and we've eaten just about a huge chunk of time just there. Here is something they call the general case. Suppose we divide a2x to put equation in the standard form. It sounds like just like what we're doing with a linear equation. Okay, because I changed things, I have to get my pen back. There we go. Okay. So we're going back to this form. Y, except it's not quite the same. Y double prime, okay, let me back up. They start in the middle of something and don't do a good job explaining what they're talking about here. Okay? Your equation 1 that we had at the top of the previous page says A. This is so irritating. Okay. Okay, there it is. Second order differential equation. A2 of x, y double prime plus a1 of x, y prime plus a0 of x, y is equal to, and they go back to the homogeneous case or homogeneous case. Okay. Now, this almost sounds like what we did back in chapter 2 with linear equations. what we're going to do is divide everything by a2 of x. Remember, a2 of x cannot be 0 for any x's in the interval. If it was, then this isn't a second order differential equation. It's a first order. Okay? So it can't be 0. So therefore, since it can't be, it's legal to divide by a2 of x, because you're not dividing by 0. Divide everything by a2 of x. If you divide 0 by a2 of x, you still get 0, right? Okay? So what you have now is y double prime is equal to some p of x, plus some p of x, y prime plus some q of x, y, now that's equal to 0. All right? Now, p and q are continuous on some interval I, okay? All right. Daniel's here. 10 o'clock scholars. Okay. All right. We're on, in Chapter 4, Higher Order Differential Equations, 4.2, Reduction in Order, page 133. Okay, general case, top of the page. This form they're calling the standard form. Now, this is standard form for a second order differential equation. And they're claiming here P and Q are continuous on some interval I. Now, you have to be careful of that because you just divided by a2 of x. Now, certainly a2 of x can't be 0. We already had that given, but so I guess everything's okay. So yeah, those are continuous on some interval I. Let's suppose further that y1 is a known function, just like we had before, of x, is a known solution, okay, on I, that interval I, and that y1 of x is not 0, okay, for every x in the interval. Okay. Y1 can't be 0. Now, I don't like their word here. So y1 of x is not equal to 0 for every x in the interval. I would prefer if they said for any x in the interval. It sounds like to me they're saying it can't be 0 for all the x's. Well, can it be 0 for one? No, it can't. Okay, for any x in the interval. Okay, so then we can define a new y. We were calling it y2, but they're just calling it y now, is equal to u of x, y1 of x. Okay? Of course, that y is also a function of x. Now, all that stuff we just did before, we do it. Okay? Now, we take the first derivative, we take the second derivative. I hate to go through all that, but let's do it, okay? If this is that, okay, then y prime is, you tell me.
I want to say, like that one before, probably.
Yeah, exactly.
U of x, y prime is y.
Y1 prime of x.
Plus u prime of x.
Y1 of x. Okay, good. And y double prime.
U prime of x, y prime of x, or y.
Yeah, got it.
Plus plus u double prime of x, y1 of x, plus u prime of x, y prime of x,
Got it.
y sub 1 prime of x.
Yeah. Right. Now, notice again, these two are identical. So we can rewrite that as, I'm going to start with the u double prime of x, y1 of x, plus 2 u prime of x, y1 prime of x, plus u of x, y1 double prime of x. Okay, so there's your y double prime. Okay? They did it in reverse order that I did. They seem like they do everything backwards from what I do, but it's okay. All right? Now, with that in place, I'm going to go up and erase my top line here. Because we're through with that, we're going to be using the form that's below it now. But I don't have room to write, so I'm coming up here to write. And I'll get it back in the order they do. So what they have here, y double prime plus p of x, y prime plus q of x, y equals 0. Okay? Now, going to plug in this y double prime down here. Like I said, I'll change it back to the way they have it. This would be u of x, y1 double prime of x, plus 2 u prime of x, y1 prime of x, plus u double prime of x, y1 of x, plus p of x times y prime, which is u of x, y1 prime of x, plus u prime of x, y1 of x, plus q of x times y, which is u of x, y1 of x, and that's equal to 0. Okay? A lot of blah, 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 right? Now, here's where the magic happens. Okay? We're going to rearrange these terms somewhat slightly. Okay? I'm going to leave this term alone, u of x times y1 double prime of x, right? I'm going to look for my next u of x. That's right here, this one. Plus p of x, y1 prime of x, right? We've accounted for this one and this one here with the p of x multiplied through, okay? And my next u of x is going to show up here, and that's going to be plus q of x, factored out the u of x, and that just leaves me a y1 of x, right? That accounts for this term. You got it? Okay. I think you should have gotten your tea. That seemed to help you more than the water, but okay.
Well, the tea that had sugar in it. I like hot tea, but
Oh, yeah. Okay.
hot green tea's the best.
Right. Okay. So I've accounted for those three terms. Now I'm going to do the rest of them. And doesn't matter which way I do it. I don't guess so. Okay. Plus, here's a u double prime of x, y1 of x, that's that term, plus okay, what they're going to do here is take this term and combine it with that term. Now remember, that term has a p in it, so that's going to be a 2 plus p of x times u. There, I did the mu. You got me doing that, didn't you? Okay. U of x, or u prime of x, y1 prime of x. Okay. That accounts for this term and that term. And now that's all, isn't it? Yep, that's all. That's equal to 0. Okay. You wish. Okay. Now, here's where the magic happens. Okay? y1 of x is a known solution for this differential equation. Remember, that's where we started. It's a known solution. That means when you put the y1 in here, you get 0, right?
Yes, sir.
Okay. Well, looky here. Right here, this is y1 double prime plus p of x, y1 of x, y1 prime of x, plus q of x, y of x, y1 of x. This part right here is 0 from this line right here, because we know it's a known solution. So this part right here is 0. So this mu of x, u of x disappears as well. So that leaves us with simply this equation, u double prime of x times y1 of x plus 2 plus p of x times u prime of x, y1 prime of x is equal to 0. Okay. Now, we do the same thing we did before. Since here in this new equation, so I think I've used this now, so I'm going to erase the rest of this. Okay? Because we've already used this. We've got it where we want it. This is just repeating the same thing we did in the first example, but only for a generic case, not a specific problem. And that's what gives it. Oh, I meant to erase that too, didn't I? Okay, sorry. All right, sorry. Now we're through. Okay. Now, at this point, we do the same thing we did before. Okay? Notice when we eliminated that, you also eliminated u of x, because this thing's equal to 0, so the u of x disappears. So now we only got u double prime and u prime. You have no u of x anymore. So that's why we say let w of x equal u prime of x. Then w prime of x is equal to u double prime of x, and you can plug back in and get a new equation. Okay? Here's your new equation. Oh, I'm sorry. I got lost in where it was. There, it's a new equation. Right here, y in the reverse order again, y1 of x times w prime of x, okay, plus 2 plus p of x times y1 prime of x w of x, because that's what u prime is, that's equal to 0. All right. Now,
Question, is that P of X, is that the same P of X we learned in chapter 2, I think?
yeah, okay, that's what I was saying before. This looks just like we did when we did linear equations, a first order linear equation, except we didn't have a q of x in, okay?
No.
So it's come about the same way. We divided by the leading coefficient function, and so it come about the same way, but are we going to do the same thing?
Yeah.
Awfully close to it.
So we're going to take the interval.
Okay, you're right on the money, and here's, since you've already jumped to it, I'm going to jump to it because we're running out of time. Here's what your solution is. Your y2, okay, I'm sorry, I guess I won't jump that far. Let's jump this far though. Okay. That u of x, all right, I'm sorry. I'm jumping too far again. Notice the other thing you lost was the q, okay? And if I skip too much, it's not going to make a lot of sense. So let me go back and pick up where I left off. Okay. Okay.
Sorry, I jumped.
No, I wanted to jump to the bottom line, and I will do it in just a minute. But let's carry it as far as we can. Let's get what we've got here. Okay, we've got y1 w prime plus 2. Now what they do here is pull the y1 I think I lost something somewhere in translation here. And I am sorry, I can't see it. I've got a y1 prime where they don't. Okay? And I'm sorry about that. So I think what I'll do is just jump. Okay? What you wind up with, what they are going to do is divide everything by your y1. Okay? And then you wind up with this. dw dx plus, okay, 2 y1 prime over y1, because you're dividing by y1, okay, plus p, that's p of x, time, okay, is equal to 0. Now I skipped some steps there because one of these y1 prime should be just a y1, and so you get this, and then you differentiate this, and basically you do this. And I lost a W somewhere too. Oh, there's the W. Divide by W, okay? And what we wind up with, separation of variables, we get dW over W. Now, I like to do it on opposite sides, and that's what they wind up doing here, is equal to minus the integral of P of X. So this is looking a lot like what, as you were suggesting,
That would be, I don't know what to do with that. P.
and you got this other term here that they seem to lose somewhere here, minus 2 y1 prime over y1. And I don't know what they did with that term, okay? And then do your dx here, and they integrate both sides. But they've skipped an awful lot of steps here. Here's the bottom line. And you never should go back through all this again anyway, and we're almost out of time, aren't we? Here's the bottom line. 5 minutes, okay. You wind up with...
Bill, is that the interval of px, or is that the interval of px minus 2y?
It should be the whole thing here, and that's where they dropped this term here, and I see what they did, but it's going to be too long to go back and redo it. Let me just give you the bottom line.
Yes, sir.
Here's what your y2 is. And don't go back and try to reproduce all this, because it's easier to do with the actual problem at hand than trying to memorize a formula. You just do what it takes. But here's what your y2 is. It's your y1 of x that you knew was a solution times the integral, and this is what it looks like before. The numerator here is e to the minus integral of p of x dx. That looks like it did before, right? Okay. The difference here is in an integral, and what the denominator is y1 squared of x. And that whole thing is then done at dx. So you have an integral in an integral. And don't go back and try to reproduce this, okay? It says it makes a good review of differentiation to verify that the function here is and that they're linearly independent on any interval. But guess what? We're not going to go back and reproduce this every time, okay? Now, that is your equation 5, and that's what you're going to use. Now, again, the P of x, as you pointed out, is a lot like the earlier P of x. And what did we do with it? We integrated it, and I can't remember now if we had a minus sign. Now we do. And e to the minus that integral is your numerator inside another integral, because you had second. This is the second order differential equation. And in your denominator, you have your y1 squared. You have your y1 of x out here, but you have y1 here. You can't cancel anything because this is integrated, and then this is multiplied by the result of that integration. So don't be tempted to try to cancel something out. You can't do it, okay? But that's how we're going to, this is called your reduction in order. And we'll start next time with example 2. I wish we could have gotten to it today, but we ran out of time. The homework exercises here, you can start trying to do some of the odds 1 through 15. Okay? Now some of those with hyperbolic cosecants and things like this, I would skip those or write what they stand for, because those are rather bizarre. or you can use them however you want to. We'll pick up the rest of those next time. And we're going to finish 4.2 and move on to 4.3 pretty quickly.
We'll get to 5 too?
So those,
We'll get to 5?
We'll get to 5? I don't think so.
Okay.
Because this is a very long chapter.
That's fine.
Yeah. We're going to do 4.3, which is really nice. You actually start solving equations, and then 4.4. And at that point, I think that may be as far as we get. 4.5 we're not going to do. That's a different approach. It's just like 4.4, but it's just a different approach. And if we get any further, we'll try to get in the 4.6 variation parameters. You can have that if you want to. It was last year's.
Well, no, I saw someone from Auburn on there.
Yeah, right.
You got Jared.
Yeah. Someone put those in my box. I brought them up here. You can have it. They're going to get thrown away. Yeah.
Well, I mean, he ain't even play for us anymore.
He doesn't?
No.
Did he graduate or did he get drafted?
He drafted.
Okay.
Phoenix Suns.
Second?
Phoenix Suns.
Oh, really?
Yeah, it's
deal.
not a good team. Yeah. In Arizona.
All right. Good deal. I hope you feel better.
Thank you, sir.
All
I'll
right.
see you.
Did you need something?
No, I thought you guys were talking about something that I need to know.
Oh, no. Yeah. Well, the thing about what we're going to cover, good for you to hear that.
Okay.
All right. Good deal. Have a good weekend.